Hey, Hammy here, back with the last section of Chapter 2 on Organic Chemistry, Section 2.3, in which we will talk about the properties of water. We'll look at properties of water, why water is important for life here on Earth, and then also properties of acids, bases, and the pH scale. First off, we all know water is important for living things. You know, you and I both need water to stay alive. We think, well, what's the importance of water? You know, the water, we call it the blue planet. We call Earth the blue planet. About 75%, 3/4 of the Earth's surface is covered in water. But of all the water on Earth, kind of an interesting piece over here, of all the water on Earth, so total water, 100%, 97% of that is saline, which means salt water in the oceans, which most living creatures, plants and animals, cannot drink. Okay, other than some of the sea life that lives in that water, you can't drink salt water and stay alive. We need fresh water, which is only about 3% of the water here on Earth. Now, of that 3% fresh water, notice 68.7% of it is frozen. It's in ice caps and glaciers. Only about 30% of it is, and then about another 30% is groundwater, okay, in aquifers and things like that underneath the ground. Actual surface water, lakes, swamps, rivers, we're talking 0.3%. One of the reasons in Bio 2 why we spend time studying our local streams and our watershed, because that water that we need to survive and we use to drink, and plants and living things that live in it, is a very, very 0.3% of the 3% of the total water on Earth. So that water is very important, and we want to look in this video some properties of water that make it important for life, why we need fresh water. First off, let's review the water molecule, because there's something about it that gives its properties that helps life on Earth here exist. Okay, so remember that water is H2O, 2 hydrogens, 1, 2, and an oxygen. 2 hydrogens and an oxygen. And this bond right here, the oxygen has 6 valence electrons, needs 8 to be stable. Hydrogen has 1 valence electron. Because it's so small, though, it only needs 2 in that first level. So oxygen is sharing an electron here, and also sharing an electron over here. That's supposed to be an E. An electron over here with another hydrogen. Okay. Now, in theory, the oxygen and the hydrogen, a covalent bond, those electrons should be spinning around the oxygen and then around the hydrogen about equal parts of the time. However, oxygen has a higher electronegativity. In other words, it has a higher attraction. The oxygen, has a higher attraction for the electrons. Okay, so they're not equally shared. The electrons are going to be spinning around the oxygen more times than they are around the hydrogen, which, if you have more electrons kind of around the oxygen, we say the oxygen side of the molecule is going to be slightly negative. Okay, Greek symbol, Greek letter sigma, so sigma negative, slightly negative. Okay, not quite like an ion's charge, not quite that strong. But this side of the oxygen molecule is going to be slightly negative. The hydrogen side's over here going to be slightly positive, slightly positive. Okay, because oxygen has a kind of a negative and kind of a positive side, we say that water is a polar molecule. Like we have a north pole, south pole of the Earth. We have a negative pole, positive pole of the water molecule. And remember, dating world, opposites attract. So when you put these water molecules together, okay, over here this hydrogen is slightly positive, This side is slightly negative. Okay, negative, positive, sort of attract. So they will form these weak kind of attractions between the water molecules called a hydrogen bond. Because normally it's with hydrogen. Hydrogen's kind of a wimp. It doesn't fight for its electrons. It kind of is a pushover. And so oxygen just steals the electrons most of the time. And hydrogen's kind of left out to dry. So it tends to have this positive charge. And so the positive ends, hydrogen ends of the water will stick together, and pretty soon you start to form this ladder. And this sets up several properties of water that are very important for life. Okay, the first property of water that makes it important for life is this high boiling point. Okay, to get from the liquid stage and to really break those molecules, those water molecules apart and put them in a gas stage, okay, the molecules have to be further apart. Okay, there's this attraction between the water molecules, okay, that makes it hard to break them apart. That gives them a high boiling point, 100 degrees Celsius or 212 degrees Fahrenheit, which is good. If you look at a picture of the Earth, you see a lot of blue, okay, the blue planet we mentioned earlier, because it's liquid, and we need that liquid for living things to take in. I wrote in my notes here, rubbing alcohol will boil at 180 degrees Fahrenheit, which is about 82.6 degrees Celsius. Okay, so much lower. Acetone, which would be like nail polish remover, has a boiling point of 133 degrees Fahrenheit, which is about 50.5 degrees Celsius. So if living things depended on acetone, a lot of places on Earth they couldn't get liquid acetone. On a nice hot sunny day, it would just evaporate really quickly. It would boil off. It would go to the gaseous stage, and it would be hard, and we'd have a whole bunch of acetone clouds, and not these big oceans of acetone like we have big oceans of water. So this high boiling point really helps it to stay liquid at most of Earth's temperatures, so that it's accessible to living things. Key point number 2, or key property number 2, is that ice floats. Remember, ice is just solid water. Water in the solid state, it's frozen. Okay? Water is actually most dense at 4 degrees Celsius. Okay, now you remember 100 degrees Celsius is boiling and 0 degrees Celsius is freezing. So you'll notice that water is most dense actually just before it freezes. When it freezes, there's something that happens in that crystal lattice that it actually kind of expands. It becomes less dense. Why is that important for life? Other than when you go to a restaurant, it makes it annoying because the ice cubes are always hitting you in the nose when you try to drink your soda at the restaurant. If you live in a pond or a lake or something like that, what happens in the winter? Okay, yeah, look, ice. Okay, snow and ice pile on top. Okay, so in a lake or pond, you get this layer of ice across the top. If ice sank, what would happen as it got colder and colder? The bottom would fill up with ice and the whole pond would freeze over. Kind of hard for the aquatic plants and animals to stay alive in that. When ice floats, however, you get this thick layer of ice across the top that will actually help insulate the rest of the pond, so the fish down here can swim around where it's still really cold and the fish kind of slow down. If you've ever been ice fishing, it's kind of hard to get them to bite sometimes because they're kind of lethargic and slow, but they can maintain life. Okay, they can stay alive in 4-degree water. Whereas if it were solid ice, if the pond would freeze solid, probably wouldn't happen. So very important for aquatic ecosystems, lakes, ponds, streams, rivers, that the ice forms across the top and doesn't sink to the bottom. Point number 3 is that water is a good solvent. We actually oftentimes nickname it the universal solvent. Again, bad handwriting, sorry. Universal water, universal solvent. Okay, so over here, here's a crystal of sodium chloride, okay, or table salt. What happens when you dissolve salt in water? Well, here's our water molecule. Remember, the oxygen side is slightly negative, and the hydrogen sides are slightly positive up here. Okay, salt is actually made up of an ionic compound, Na plus Cl negative, that are stuck together because of their charges. Electrons have transferred, they have a charge, and now they're going to stick together. When you put them in water, look what happens. Okay, the oxygen sides of the waters will tend to pull off the sodium ions and kind of surround them. And the positive hydrogen sides, see here the hydrogen is all facing in, hydrogens are slightly positive, they will pull off the Cl negative ions and kind of surround them. And you can put salt in the water and it will slowly dissolve, right? It'll pull it apart. Okay, this is important for cellular reactions. Our cytoplasm is mostly water in our cells, and it helps dissolve things so reactions can happen. Okay, your body and your cells are about 60% water, so almost 2/3 of you is water. The two most important chemical reactions in living things, and I want you to scribble these down in your notes because these are important. We'll do the cell chapter next, and then we'll spend some time also looking at these processes. Very, very important. Where we take low energy photosynthesis, we take low energy carbon dioxide and water, and we dump in energy from the sun to make this high energy molecule called glucose, C6H12O6, which we talked about earlier this chapter, and a byproduct of some oxygen. If you look at cellular respiration, we're taking the energy from this glucose. So here's our glucose. They're just reverse of each other. We breathe in oxygen. Why do we need oxygen? Okay, this oxygen helps break apart the glucose, and actually it accepts some electrons at the end of the stages. We break off the carbons as CO2. The electrons end up in oxygen as water, and the energy in glucose is broken off into energy to help us move, to help us think, and all those cellular processes. Okay, this is looks like kind of a simple equation here, but there's like hundreds of steps going from reactants to finished products. And all of those reactions happen in the cytoplasm of our cells, which need this water to kind of dissolve and suspend all these chemical reactions that are happening. So water, being a good solvent, gives our cells a place for very important chemical reactions to happen. And finally, the fifth property your book gives is the high heat capacity. What's high heat capacity? High heat capacity, because these water molecules have a slight attraction for each other, it takes a lot of energy to break those molecules apart. It kind of goes back to that first one of water having a high boiling point. This allows organisms to thermoregulate. Okay, we often know that as sweating. When you start to get too warm, okay, your sweat glands here you can see the sweat on their skin there, puts water on the surface of our skin, and the heat from our bodies, our body heat, is used to move that liquid water, take those molecules and break them apart into gas water. So it draws sort of the heat can escape our bodies, and sweating helps us cool. Okay, after we've been jogging or running, okay, or doing something, or sitting in the sauna where it's really, really warm. Okay, this helps bring our body temperature back down, important for maintaining homeostasis. Also, at an ecosystem level, water is very important in coastal ecosystems, because if you are by a very large body of water, that water changes temperature very slowly. So during the day, if you've ever been at the beach, the sand gets super hot and the water feels cold. And then you go back out at night, the sand is chilly and cold, and the water feels kind of warm. Okay, that water doesn't change temperature as fast as the land does. And as air and breezes, wind blow across the water, they will help regulate a lot of the temperature along coastal ecosystems, and so you get this nice even temperature. Okay, it kind of cools the land during the day and then kind of warms the coast during the night, and so you get less temperature fluctuation, and that's very important for homeostasis within in some ecosystems, besides just at the organism level. Okay, so I hope this kind of helps you understand why we as life on Earth have to have water. The next video will look at some properties of water that causes things like acids and bases and why that is important.